So once more, a very warm welcome to the Kiel Imaging Seminar. We're very happy that our audience is with us, and we are very, very happy that David Norris is with us today. Please let me introduce him quickly. He, with a distinguished career spanning groundbreaking contributions to pulse sequence design, fast imaging, diffusion-weighted imaging, and high-field MRI, David has been instrumental in pushing the boundaries of neuroimaging, from leading the development of the 3T system at the Max Planck Institute in Leipzig to co-founding the Erwin Hahn Institute with one of Europe's first 7T scanners. His work has paved the way for advancements in ultra-high field imaging. Currently, David is heading the Dutch National 14 Tesla initiative, and that's why he is today. He's as well part of the Citrus EU network, developing focused ultrasound for brain stimulation within the MRI. He's a fellow of the Institute of Physics, International, the ISMRAM and the ESMRAM-B, and a scientific member of the Max Planck Institute for Psycholinguistics in Nijmegen, and an adjunct professor in Vienna. Before we start, please, everyone, keep your questions till the end, and we will just have a very nice discussion around. David, without much further ado, the stage is yours.
Okay, thanks very much for the nice introduction. I assume, just give me a verbal sign that you can hear me and everything's good with the slides.
I hear you perfectly.
Okay, and then we'll move
I have
on.
issues. Yeah, I have issues seeing your slides, but that's likely because of me and not of you.
Is anybody else having any issues?
No, it's fine for me.
Okay, it's fine for you. Then we'll
Perfect.
assume that this is going well, and I'll just go through it. Well, I'd like to talk you through a little bit about the whole procedure, which ended up with the Dutch 14 Tesla initiative. And I think my first disclaimer is I'm only the head of a very large enterprise to which very many people have contributed, as you will see. So the Netherlands signed up many years ago to make money available for scientific infrastructure, and the way it was funded up until the current government decided to cut it was 100 million euros every 2.5 years. And there have been discussions in the Dutch community for some years about getting an extremely high field system. As I think a lot of people will know, the Netherlands was a pretty early adopter of 7 Tesla. And we put in a proposal in 2019, and we got to the interview round with a great deal of excitement, and we got rejected, which left us 2.5 years to lick our wounds and rewrite the proposal and resubmit it. In the revised proposal, we went for having 3 scientific pillars. So we oriented ourselves around the science, which was basically neuroscience in its purer form of cognitive neuroimaging, brain disorders, and medical applications, which would mean basically X-nuclei, whole body, and anything outside of these. And you will see, in some ways, this maps the kind of development trajectory we have for the scanner as well. And it was really quite a large effort. I mean, the proposal itself was about 50 pages. I think 86 scientists contributed in some way via the sub-projects where we gave sort of exemplary applications for a 14 Tesla system. And I'll describe some of these today. As you've probably realized, I have nothing much to offer you except sort of prospects and insight on some of the design. But I think it's really a very exciting project. We're all very motivated on it. And the second time round, we were scored #1, right? So we were the best in the whole round. I think we had this leap because we we could either have resubmitted the proposal we put in 2019, or we could have rewritten it, and we went for a kind of double or quits. So in 2019, we went for a more conventional low temperature superconducting magnet made of niobium tin, and this time we went for a high temperature superconductor. So we scored quite highly both on the scientific part but also on the technical innovation. And we only got there because everybody pulled together very hard. So the Netherlands has the advantage, at least if you take this part of it, it's probably not much larger than Greater Los Angeles, which means everyone, even if you're not working in Nijmegen, where I'm working, which is a large red circle here, everyone has a chance to access the scanner within about an hour and a half train journey max. And because of the early adoption of the 7 Tesla scanners, we have a lot of really well-known international experts, ranging from hardware through to applications. So Andrew Webb, Dennis Klomp, who were the other two people with me who really did the sort of heavy spade work, and an enormous range of neuroscientists and other people who are well known in their respective fields. And since the grant was awarded, Jose Marquez has been in Nijmegen now for 10 years as well, but we've now recruited Martijn Close, who's really doing an awful lot of work on making the 14 Tesla develop. So it wouldn't be Dutch without a lot of committees. So it's a way also of distributing expertise, and it's a way of making sure everyone stays involved. And actually, in my opinion, it's a way of making brave decisions as well, because collectively we came to the conclusion we would go for a high temperature superconductor, whereas a single person may have balked at it. But we have basically the scientific board, we have a hardware committee, and since then we've produced committees for almost every single endeavor, including the magnet. There's a special magnet committee, which brings in international expertise from outside. Neoscan, based in Magdeburg, are building the magnet. Philips providing the console and quite a lot of troubleshooting expertise. Tesla are providing the gradients, and Wavetronica, which is a spin-off based in Utrecht, will do the RF. Now, in real estate, everyone says it's about location. Actually, in some ways, in science, it's about location as well. And we had a lot of discussion in the Netherlands about where should this darn thing go. And in the end, we decided for Nijmegen. Why did we decide for Nijmegen? Well, this is an aerial view of the campus, and it won't surprise you to learn that the red rectangle is where the MR scanner is going to go to 14 Tesla. But if you know Nijmegen, across the road here is where the Donders Center for Cognitive Neuroimaging is. We have over 1,000 people in Nijmegen working on neuroscience, which makes us very strong in that area. And this is the boundary, in some ways, between part of the university and the University Medical Center. So this is really a near ideal location, both for doing neuroscience and for getting direct medical applications. There's a tunnel under the hospital which goes straight into this building where the magnet is. Another thing which is really extremely fortuitous for us is that this is a kind of plan flipped on its head to match the building, but this is where the magnet will come. X marks the spot here. And because a high temperature superconductor is a more compact magnet, it's only about just over 2 meters long, the entire magnet, the footprint of the magnet is actually quite small. And it was almost like, as one of my colleagues said to me, it must have been destiny, because the stray field fits perfectly inside this garden area, which coincidentally is set 2 meters lower than the rest of the ground around it. So we have a natural sort of encapsulation of the stray field already in this system. And there were some amazing artistic impressions going around from one set of architects at the time we got the grant, which I've now removed, but I'm sure many people have seen them. We now have a different architect, so we have a different idea for what the system is going to look like, and we're concentrating on making it not very intimidating. So we will try to actually have a Faraday cage which has quite a lot of glass in it, so that people are not feeling totally intimidated by a very large magnet. Our magnet will probably be heavier than first anticipated, but it's still not much larger than a first generation 3 Tesla system. And of course, once you get inside, this is the sort of futuristic view of how the architect is seeing these things. I'm sure the artist's impression was actually what won the interview for us when we went to the Dutch Science Foundation for the interview, because it looked so amazing. But anybody knew about MRI knew it was a completely unrealistic mock-up of an MR scanner. But that's life, I suppose. So, okay. Going over to the more scientific aspects, well, why are we going to 14 Tesla? And I think for all MR scientists, the answer is pretty obvious. We want to gain the sensitivity. And this is a very well-known publication from the Tübingen and Magdeburg groups showing how going up from 3 Tesla to 9.4, in their cases, you get a superlinear increase. And if we go to 14 Tesla, we are, roughly speaking, 3 times more sensitive than a 7 Tesla. Some people will claim even 4 times, but I'm not going to go that far, or 13 times more sensitive than a 3 Tesla, which leads me to my little economic law that the price is actually very good that we're paying, because it seems to me like if you look at the list price of a 7 Tesla, multiply it by 3, you will land up pretty close to what we're going to spend on the 14 Tesla. Or indeed, if you would take the list price of a 3 Tesla, multiply it by 13, you'd end up with almost the same sum of money. So maybe there's some hidden rationale behind the MR system pricing, which has hitherto escaped us. Why go to 14, specifically 14? Well, 7 Tesla has become an established field strength. 9.4 hasn't really. And the 11.7, there's one in Paris and there's one coming in Nottingham. So that will be interesting. But the 11.7s have been built because of the limitations of niobium titanium wire, right? So that's the highest field strength that a conventional niobium titanium superconductor can get to, because there's a critical field strength for superconductors as well as critical currents, etc. So the 11.7s in that sense have been driven by necessity, whereas if you want to make a significant step up from 7 Tesla, well, historically, people went from 1.5 to 3 to 7, and you need to go up in steps of 2 or 3 to get a qualitatively different performance. And so 14 looks to us like a good place to be. It's a factor 2 more than 7, and it's far enough above 11.7 to have been worth the effort. And hopefully we move into a different biological domain. When I got 5 minutes to pitch this project to the Dutch Science Foundation, I claimed we were going to make a mesoscope, right? So that we would investigate things on a biologically relevant domain. It's not a microscope, but it's something in between. And whether we can substantiate that is another matter. But first of all, let's have a look at the magnet. So in contrast to what we originally were going to do, we've now moved to 2nd generation high temperature superconductor, which is REBCO. So the critical field for this superconducting material is around 30 Tesla. So building a 14 Tesla is about the same as building a 6 Tesla using niobium titanium. So we can actually build a compact magnet. But of course, no one has done this for MRI before. So we are taking quite a risk in this endeavor. Why has it now become feasible? Well, a lot of developments in HTS, high temperature superconductor, have been driven by nuclear fusion. So this is why there are now large-scale manufacturing capabilities for HTS. It's nice for us. We don't need a liquid helium bath, and it has other advantages. We would operate at about 7 Kelvin, but we can get up to about 20 Kelvin without quenching. We have to run the magnet in driven mode because the Repco wire is not delivered in a single batch of 480 kilometers, which is what we would need for this magnet, but it's delivered in lengths in the sort of let's say order of magnitude of hundreds of meters, but then you have to join them up, and then there's no superconducting way of joining these things up, so you have to drive the magnet to keep a stable field. But if it quenches, you don't need to find 5,000 liters of helium to cool the thing down in the first place, and you can because the superconducting wire is not potted in epoxy, you cannot actually unwrap things and reuse them. Like I pointed out before, we don't need shielding, and because we have a broader range of temperature operation before we go critical, there's a reduced risk of gradient magnet interaction. So these are all pretty positive things. And as I said earlier, we end up with a sort of normal size magnet. The fact that we haven't done this doesn't mean you can't do it. So at least in the fusion field, there's this 20 Tesla thing, which is a tokamak for fusion. So it's a completely different magnet, but it does show that you can build large magnets using this technology, which is a kind of sign of hope. In terms of the rest of the equipment, I won't say we've been conservative, but we're starting off with a whole body gradient set, but we will have full whole body coverage in a diameter 60 centimeter, 120 millitesla per meter, slew rate 250, which is pretty good. And one of my kind of requirements was we should be able to do continuous EPI with the system, because bringing the system to Nijmegen, you want to use it for functional neuroimaging, and you don't want to have all sorts of constraints on it. We're putting a lot of effort now into designing a specific gradient once we know what the magnet design is, so that we minimize gradient magnet interactions as far as possible. And we expect with the other positive features of the magnet that this will not be an issue with us. And of course, we get shims up to third order. In terms of the RF, we're taking a two-step approach. So obviously, it's going to be quite challenging building coils at 600 megahertz. So we'll start off with head coils, where we've only budgeted head coils. People who want to do other body parts are going to have to find grants for building their coils. But of course, we'll share all the know-how and build up from 832 to 1664 in the second stage. And we'll have a 32-channel local shim array as well. So we hope to be able to get around a lot of the potential disadvantages of poor static magnetic field homogeneity using the local shims. So roughly to get close to where we would be at 7 Tesla in a system without a local shim array. And we will be equipped both for proton and for X nuclei in advance, but like I said, no coils. And some of the simulations which have been done actually by Eindhoven, showing how to build, how we go from 300, I mean, I'm not really interested in this area, but this is 600 megahertz where we will be, kind of indicating we probably won't have such bad problems with SAR as the classic interpretation that everything would go up as B0 squared. Of course, we have a lot of collaboration already with Paris and Nottingham. Paris have already been showing on the benefits of parallel transmission, and we will have to get a PTX system working really well, of course, at 14 Tesla to get good coverage of the brain. If we look at what we can expect in terms of key relaxation times, of course, we get longer T1s, we're getting shorter T2s and shorter T2 stars. So for tissue, we will probably be looking at TEs of around 15 milliseconds for doing fMRI. The T2 of venous blood may well get so short that we don't see it in fMRI anymore, which was previously an argument for going to 7 Tesla, but we will have to see. Things get short, but they don't get so ridiculously short that you can't image them. But of course, we're going to be challenged in getting a lot of high resolution images out of the system in short TE. So there'll have to be quite a lot of segmentation. So how are we going to do it? Well, start at the brain and work outwards is always the way developments go in MRI, and we're going to keep to the low power deposition variants, of course. So inversion recovery, if we can get an inversion repulse with then low flip angle readout, gradient echo EPI or similar, and spectroscopic imaging, which as you will see later is quite attractive to us. And you know, sometimes you want to get higher resolution than's been achieved, and of course in other times you want to trade that off for shorter acquisition times just to make things more feasible. So if we would look at anatomical imaging, this is a beautiful image of the brain obtained by Oliver Speck in Magdeburg, and you can't appreciate how beautiful this is because it's got a resolution of 250 microns. Probably we won't get any better than this. The thing is, of course, this data set took 8 scanning sessions to compile, and then all the data had to be sort of cobbled together to produce these beautiful images. Whereas if we're a factor 3 more sensitive than 7 Tesla, in principle, then we've got a factor of 9 in the acquisition time, assuming we can sample enough data points. So it could be possible to get this kind of image quality within a single session. And then, of course, you want to start looking at subcortical nuclei, or you want to start looking at structures like stripes of Bayer, which are within the grey matter. And these are examples already from 7 Tesla, from Utrecht, but we can hope to move on to doing this kind of thing routinely and moving outside of the parts of the cortex where there's a strong myelinization. If we want to start looking at brain networks, then this is of course very characteristic 3 Tesla data. And if you're looking at this, of course, you can see brain networks spontaneously coming up because different areas are co-activating when you look at things in the resting state. But currently, fMRI is blind to the direction of interaction between different brain regions. So if you want to start into investigating this, you need to move not to this, but down to this level. And this has been one of my research themes in recent years, but a lot of people have got interested in this. So if we look at the different layers, histological layers in the cortex, they actually have different input and output functions. So if you start looking at levels in a hierarchy, there are quite advanced theories about how different regions interact when you're getting a feed-forward line of information flow or a feedback line. So by looking at differences in activation profiles, you can see whether you're looking at feed-forward or feedback information. At 7 Tesla, we are looking at roughly 3 layers, sorry. But when we get to 14 Tesla, we would anticipate being able to look at about 0.3 millimeter functional resolution, which would get us about to the level of splitting all the main layers from each other. I was saying about spectroscopic imaging, and one of the things we got quite excited about when we were building up to this grant was the realization that in theory, you should be able to measure GABA with about 18 times the sensitivity of a 7 Tesla system. Because we have higher chemical shift dispersion, we can leave out the editing, we can go to short TE, and we've got the greater sensitivity anyway. So we're kind of imagining that when we get things running well, we'll be able to get chemical shift images of GABA and glutamate at about 3 to 4 millimeter isotropic resolution in minutes, which will mean we can start looking at the excitatory inhibitory balance in the brain in more of an imaging context. And there's been quite a lot of interest in GABA in neuroscience in recent years, because it is measuring something different than what BOLD is measuring. But of course, even at 7 Tesla, we have large voxels and normally only a single voxel. We've also got very strong groups looking at ex vivo imaging, for example, in Maastricht. And of course, this is one of the things we will put a lot of emphasis on in the early years, because we don't have to worry about the safety considerations in ex vivo. So again, we can use this to develop a lot of hardware and methodology without anyone being at risk, and scan for long times in the early period of having the system operational, and hope then to get real improvements in what we can see in tissue samples and indeed whole brain connectivity imaging. Once we get up to routine operation, we would like to get a large sort of baseline sample from healthy volunteers. We've had something called the Healthy Brain Initiative in Nijmegen, which scanned about 1,000 local residents several years back, and we would probably try to repeat the exercise, but then doing the things which are different than what the Human Connectome project could do. So, of course, high spatial resolution in the resting state, the anatomical imaging, the spectroscopic imaging. So this would be a very useful and important resource once we get up to a stage of having robust measurements. If we look at some of the other areas of science that were included in the grant, then this is, of course, kind of a bit let's say, prospective, but there are real hopes of making advances here because of the ability to look more at dynamic processes, getting back to looking at abnormalities at the molecular level. So one of the things the people like Rick Helmig are interested in are looking at locus coeruleus, where you can see that it's a very important organ, but it's barely visible. This is ex vivo, a very long scan at 7 Tesla. This is what you get with 3 Tesla, and this is histology. So there is some hope, if you look at the ex vivo, that we may be able to get sufficient information to interrogate subcortical nuclei like the locus coeruleus. There's also interest in looking at small vessel disease, for example. And again, this is only hope based on what people have been able to see, for example, ex vivo, and comparing to biopsies where you can start picking up abnormalities next to small vessels as you go to finer and finer resolution. Obviously, you will at some stage get to be motion limited. So we kind of anticipate that the limit of spatial resolution that we'll be able to achieve is probably not quite 200 isotropic. I think probably 250 is where we may end up, but we have to see. Again, multiple sclerosis is another area where we've got a whole group of people who are particularly interested in looking at lesions in grey matter. Again, the hope being that we can identify far more of these than is common. If you look at something like CEST, then as you go from 3 to 7 to 9.4 to 21 Tesla, which is obviously from the rat brain, you can see a vast increase in the information available within the CEST spectrum. And something that Tom Schreenen has been working on in Nijmegen and in Essen, indeed, is using contrast agents in oncology, where you can really identify very small metastases in lymph nodes. And we've got another group in Nijmegen, but also some other colleagues within the Netherlands who are very interested in just using fluorine-labeled nanoparticles as a contrast agent, and they work very often in animal models, but these could be moved towards humans. Again, rather speculative, maybe, but at some stages could be interesting. So when? Well, you know, the history of extremely high field systems has been, let's say, a little bit checkered. We've been very encouraged that Paris and Neurospin are on field and they're stable and it's working. So no, I should have updated my slide. It's next year now. We would hope probably maybe 2 years is the truer thing than 2026. But when we got the grant, I somehow persuaded our university to buy the magnet before we got the money from the Dutch Science Foundation, which actually meant the time to delivery started then, which was in October 23. And it meant essentially that the magnet was due to be delivered before the building was ready. We may have some slippage with the magnet, but I think we're still on a trajectory to be getting on field in the first half of 2027 with the building completed. After that, of course, safety. So nobody's going in the scanner until we've had a careful assessment of safety. So we've got one of the PI groups involved in the dynamic proposal is now examining safety. Of course, we'll look at what Paris have done in going to 11.7 Tesla and probably mirror that to some extent. But we are not anticipating that we're going to be spending years on this, but we certainly need to do a very careful assessment. So it'll probably take, I don't know, somewhere between 1 and 2 years before we would be imaging human volunteers, assuming that nothing adverse would come out of the assessments, which leaves us with this. So is this it? Am I really ushering in the final frontier? Well, maybe for the time being. I mean, it took 7 Tesla 20 odd years to go from the first installation to FDA approval and some measure of acceptance. If you want to go for a factor 2 to 3 more than 14 Tesla, then that's going to be pretty exciting, but maybe it'll take us a long time to get there. 7 Tesla has been a great success for research and pushing back the boundaries. But there's now quite a large 7 Tesla community. I think it will take quite a long time to establish a real 14 Tesla community, because if we get our system up to field and running within the timeline planned, it'll probably be 3 or 4 years before anybody else is there. And we are really very open to collaborating with anybody, or because we would like there to be a thriving community at 14 Tesla. We just see it as enlightened self-interest to be very open in our philosophy. And it's indeed the way the Donders Center for Cognitive Neuroimaging has always functioned. So, but it will take a while to get there. And like I'm kind of suggested with the first bullet point here, I'm not sure that really going way beyond 14 Tesla is sensible. We may hit physiological limits. And if you look at the increase in sensitivity with field strength, going a few Tesla higher could be possibly advantageous. But once you've established yourself at one field strength, then it's much easier to build copies of the magnets, copies of the RF coils, etc., and enjoy the benefits of having a community. So I hope that things will coalesce around 14T. Okay, well, it's very expensive, but actually, like I argued, I think it's really good value for money. It's about obtaining fundamental knowledge. So just to be clear, this isn't about some sort of elite radiological diagnosis service. And we work over a broad range of field strength. So we would like to also translate the knowledge that we gain down to lower fields. And as I was just saying, we are really very happy to become an international partner, or to host studies, or anything really, just to get critical momentum behind the system. So we're doing a lot. I think we've got a great scientific community in the Netherlands, but we are really pulling people together. It's the system, at least within the Netherlands, is free at the point of delivery. So we're not charging people, enormous sums of money per hour. We obviously have to look at funding models for people coming from outside. But again, the aim is not to try to make money out of it and most kind of setups which have had per hour funding schemes have struggled to succeed. So there we are. We want a big community. We want to succeed. We want other countries to succeed as well. And thanks very much for your attention.
All right, David. Thanks so much in the name of everyone. That was a fantastic presentation. Are there questions from the audience? Can you hear me all right?
Yep.
I can hear you.
Perfect.
I can't see anybody else.
Let me check the chat. Otherwise, I'll just draw from my plenty of questions. So you spoke of like a physiological limit to the resolution, and you mentioned like 200 microns isotropic, I assume, would be maybe the limit. We observed something maybe similar while doing dental MRI with local receive coils, where we could only go to 300, we could go to 350 microns isotropic within like 3 or 2 minutes. However, ex vivo, it looks much nicer than in vivo. And we thought as well that's like the motion. Did you concur? Do you think that's the case? And did you consider motion correction techniques?
Yeah, I mean, we will try and develop motion correction techniques to work inside the system. So yes, even pushing these to the absolute limit. I mean, if we're just talking about brain imaging, you still have pulsatile motion of the brain, which without motion of the skull. So you're going to. There will be limits to what you can correct, and the anatomical imaging community kind of sat down and said, well, what could we legitimately claim based on what we've seen so far? I mean, Oliver got to 250 microns with an awful lot of correction. I think that's feasible. Whether we can really go to 200 remains to be seen, right? 250 would already, I mean, those 250 micron data are fantastic, right?
Yeah. There's a question in the chat, but before I take this one, did you consider an open sequence development platform, or will you stick with the manufacturer consoles, Philips?
Yeah, well, you can use PulseSec on Philips as well, right? So we, for example, are historically a Siemens site. So in our group, we're using PulseSec an awful lot. So we will use some of these and open source, certainly for development, maybe translate into the manufacturer's specific implementations when we want something to work really well, because I'm not sure you always get access to all the features. But certainly for development, we will support PulseSec and things like this for people just wanting to come in and do proof of principle or development methods development work. Absolutely.
I think that would make life really easier. 501, yeah. So Mark Conradi is asking, how do you intend to temporarily stabilize this driven field?
Yeah, I mean, Neoscan actually have very good experience with their, I mean, it's in the stability of the power supply. So their 1.5 Tesla neonate scanner is actually has drift figures which aren't much worse than a normal supercon. And I mean, coming from a functional neuroimaging background, what I do know is gradient heating is a far greater source of instability in neuroimaging than actual magnet drift. So I think that's not one of the things which keeps me awake at night at the moment.
Yeah, I can see that. So again, I invite everyone to please ask questions in the chat. What is you spoke about a modular B0 shim array. Do you have plans for that, or do you have something in mind?
Yeah, we're in a design phase at the moment. So at the moment, we're looking at small coils basically placed on the cylinder at some distance from the head, but much closer than the standard shims is what we're looking at. We need to be still compatible with the wish to do fMRI and have some kind of visual stimulus that's visible. If you get too close, you start getting interaction terms with RF coils, which can lead to losses. So at the moment, there's a kind of compromise solution with the local shims being outside the head. Probably we may well only do this for the second RF coil and first see where we end up with the first one. We're great believers in starting off with the simplest possible system and then building from there.
I can see that. What line width do you expect? I mean, spectroscopy should be an awesome application.
I don't know. I don't really know what we're going to get in terms of shims. I'm kind of hoping with a local shim we would get down to similar performance in at least good areas of the brain as 7 Tesla without the local shims. It should help. I mean, some of the results from the MGH with the local shims have been very encouraging. And of course, we can also hopefully reduce distortion in if we end up using 2D EPI trajectories. It's also very useful in that context as well.
So you're thinking of really MRSI, like so?
Yeah, we're thinking. Well, I'm not with standard spectroscopic imaging, right? But over pretty large volumes. Yeah. I mean, theoretically, simplest sequences are the best if you can get them running, because they've got the highest sensitivity, and you don't have to use lots of complicated RF pulses.
Yeah, sure, I agree. Thomas Marecci is asking how long will be required to insert a human into the magnet without uncomfortable effects?
Yeah, we have a hand-driven couch for obvious reasons. I don't know. We don't have a self-shielded magnet, right? So a lot of times it's actually the gradient of the field rather than the absolute field, which is creating these effects. So if I'm optimistic, I would say we can probably go in at roughly the same speed as a 7 Tesla shielded one, or maybe a tick slower. But this is what we've got to try out on volunteers. What the physiological effects of 14 Tesla are. Well, first of all, not on volunteers, obviously on the animals, but when we build up to volunteers, we have to get experience like they did in Minnesota with the 10.5 Tesla, like they've done in Paris with the 11.7. I don't think it'll be prohibitively long, but I think we'll be putting people in quite slowly, is my short answer. Nice you could join as well, Thomas, from a different time zone, I think.
Did you look into other chemicals except GABA?
Well, other metabolites. I think for the thing that got the neuroscientists excited was GABA. So that was pretty much in the neuroscience part of the application. I mean, there's a lot of spectroscopy expertise in the Netherlands, particularly in Utrecht. They are very interested in getting on with X-nuclei. It's not really my area of expertise, so I'm not going to start blabbing about that. We did have some sub-projects using X-nuclei, but this will follow on. My kind of goal in this is go route one as to proton imaging of the brain, and what you learn there will help you in every other thing you do. And once you've got something working, you've got evidence for writing grants to get other things working, right? Yeah.
But I could see that deuterium, thermally polarized deuterium and thermally polarized carbon could be very, very interesting.
Absolutely, yes. No, I mean, get the system working, and the opportunities are considerable. And like I said, we're really very open to people who want to collaborate or want to do specific experiments to making that happen.
And there you may actually see different things that you were not able to see before.
Yeah, in theory, that's true. You don't get any. Unfortunately, I mean, historically, it's the things that weren't expected were the most exciting, right? But if you ever write that kind of stuff in the grant proposal, it's on this side of the Atlantic, it doesn't get you very far.
I agree. And that's the beauty about science too, right?
Yeah.
The unexpected
discovery. So we have to have something solid and believable for the expected discovery, and still have the eyes open for the unexpected.
We have to sell the expected one. Anyone else, please take the chance and ask a question. So Francesca Vacca, I'm sorry if I pronounced the names wrongly. Good evening. Thank you for the presentation. I was curious to ask more details about how the cooling of the primary coil is envisioned.
We just have it's like a big fridge, basically. It's just a cryocooler. If you're asking about the magnet, it's a cryocooler with a lot of so we have to have copper plates going through. So it's multiple coils with multiple pancakes inside them, and in each pancake there is a copper cooling sheet, and basically you just cool it down using cryocoolers over a period of weeks to get down to your operating temperature.
So, and I guess those are just closed cycle helium cryostats, the standard industry standard. And then you just have a well insulated stainless steel or aluminum duar.
We've gone for a steel one this time, but Neoscan, because it's the first, they've been ultra conservative of having the sort of most solid possible cryostat. So yes.
Thomas is asking again, pulse tube coolers, and I think pulse tube coolers are those just standard closed cycle helium coolers, right? You have one stage or two stage ones which expands the helium. I think so, right? Oh,
yeah. To be honest, I haven't investigated it because they've also been selecting. Neoscan had a certain make of cooler in the initial offer, and I think they've moved to a different one now. So things have moved from then as well.
Yeah, but that again shows how such a large project can be realized by every industry is borrowing from each other, right?
Yeah,
it's good that we have an established cryo industry which provides the low temperatures, and ideally those don't need to be developed new.
Yeah.
As you said before, as the superconducting wire comes from fusion.
Yeah, no, but also the Neoscan have been using the cryo coolers for their 1.5 Tesla. They just need a bit more power on the 14 Tesla.
All right. If there are no further questions, then I would like to thank the audience and our speaker for tonight. Once more, thank you so much for being here tonight, everyone. It was a fantastic presentation.
Thank you.
I learned a lot.
I enjoyed presenting even from a distance.
That was great. And yeah, see you soon.
Okay.
Have a good evening.
Take care. Bye.